So this is the first example, and the first example is as follows. So essentially, we are trying to create a vector loop. Whoa, I have to mute you. So it is to create a vector loop on this mechanism right here, right? And so this is sort of like that 4-bar mechanism we did earlier, only there's a slider in here now. And what's funny is I actually have this one drawn as well. So this is something I did last semester. I drew this one because people were confused about this one, so I drew this. So we'll get to that if we need to at the end. So what I want you guys to we're gonna create the pattern for you. So this is the way that I would do questions such as this. So the first thing you shall do is you should define the vector loop. That is the very first thing you should do. And so I'm going to write that up here as define the loop. So define the loop. That should be the first thing that you do in the simplest possible way. And like I said, this might take you more tries than just one. Like you might get through the first one and you count the number of knowns and unknowns and you're like, man, this is looking really tough. Like why are there 5 unknowns but I only have 1 or 2 equations, right? You might get to that point. And so you might think, oh, there might be a better way to draw this. So then you do it again and it might get better. See? So don't get hung up on having to do it right the first time because you can make an improvement. But anyway, so the first thing we're going to do is I'm going to number these for you. 3. So how would we go about defining the loop? So once again, the point of this is to create a vector loop that accurately describes the motion of this mechanism as it turns, right? Or as this thing moves. So, as I have said in previous classes, we start with link 1 to 2, right? So link 1 to 2, the connection here, which is a revolute joint. And a revolute joint, if we go... I was going to pull up the rules, but I think everybody knows. Essentially, for a revolute link, you just start at the center of where they meet, right? Where the revolute pin is, or the revolute joint, and you just go up here, right? I think everybody can agree that that's how we should move about this one, right? That makes sense? Pretty sure everyone's got that one. So, let me darken this one a bit. So that one, and we shall call it R2 because it is the vector associated with link 2, so we will call it R2, right? Just keep it easy for everyone. Now, how do you think we should do this next one? So this is the trick. This is a bit of a tricky one. So, well, not really actually. So whenever we did that slider, you remember that slider we did the other day? You know, it was like the one that slid on the ground. Well, the only difference between this one and that one is that it's sliding inside of another piece, right? And so, how did we define the slider's motion? Can somebody tell me that? How did we define it? Like, if you put your hand across the ground, or if you move your mouse right now, your mouse can only move across your desk at a certain height, right? It cannot, like, fly off the desk unless you make it do that. So the motion of the slider has to be defined in a way that makes sense. And so now, if we look at this right here, this part, what possible motion for the slider could we put into here that it makes sense? Like here, can we go like this? No, right? Because that doesn't make sense. So Jackson is going to tell us, I think, the answer of where this goes. Like, how do we know where to put this? Follow the channel, that is correct. So, essentially, we are going to follow the channel here. And so you would pick the middle of the revolute, and then you just pick a point, right? You pick a point to stop it, because the point doesn't really matter all that much, but you pick a point to stop it at. So I'm going to say it's right here. Right? And we're going to call this one R C. R sub C. Does that make sense? Yeah, let me redraw that one a bit. Because we have to, well, so it could be 3 or it could be C. So the way you name it is sort of, it's arbitrary, but remember we still have to connect like here to here. So I was saving that for 3. But essentially it doesn't matter how you do it. As long as you put it on the paper, I don't care how you like mark these things down, right? But so the way I would do it is that if you ever have to go, if it's ever like a slider inside of something, or it's like going to the center of a circle, name it C. But once again, you could name it like this if you wanted to. You could name this one, R smiley face. I mean, it doesn't matter, name it R Batman symbol, like does not matter at all. But as long as you define it, you'll make more work for yourself by naming it R Batman symbol, but, it's the way it goes. So I'm going to call this one RC, but like I said, you guys are more than welcome to name it whatever you want, but obviously within reason. Don't name it, something really long and dumb. But RC is what I'm going to call it. And then, I'm going to draw this line down to there. So the next one, as you guys are probably aware, is that the next one that we have to do is we have to connect this and make it a loop, right? So the next obvious choice, since there's no other sliders, there's no other center points on a circle, the next obvious choice is to go to this revolute joint, right? So I'm trying to draw this straight, but I'm gonna draw it like that. Sorry. That's about as straight as the line's gonna get. Shit. That's gonna read good on the recording later. Alright, so does everybody kind of see why we chose to go there? There's no other logical place to go. There was no other mechanism part that we had to pick up in the loop. That was the only place we could have went to, right? So I'm going to call this one R3. And then I'm going to give somebody the last one. Let's give someone this a layup. Junlin, where do we go next after this? Get you feeling nice and confident today. And if he doesn't want the layup, we'll give it to somebody else. Like Sean. Sean, would you like to tell us where we go from here? Or is everybody taking the day off today? Back to the original ground. I agree with you. And follow-up question to that, Sean. How do you think we should make the coordinate system for this one? So where do you think we should put the X and Y axis? Carefully. Yes, that is a good answer. Carefully. I would say it is carefully along that same line that you just told me to make. And the reason is because we want to try to eliminate something, and if we eliminate R1's angle, then we have done a good job with our coordinate system. Wouldn't you agree? That was carefully done. So, alright, and so I'm going to remove the poop emoji right here, and that is exactly what we should have done, right? which is no surprise because I wouldn't have put it up here if you were going to do it wrong. But anyway, so this is the actual vector loop that they created, right? Oh, I forgot to add that. Never mind. So now we need to start showing, oh, they named it R31. See, once again, you know, name it whatever you want, but they actually named it R31 here. So anyway, so now we have to start going through. So this was the first step, right? You guys all agree that was the first step. We have defined the vector loop. Step 2. Step 2 is to we need to find all the variables, right? So we need to do knowns and unknowns. So we're going to go do knowns. And, why did I put a colon there? What am I doing? Plus unknowns. Oh, man. I cannot draw. All right. So, knowns and unknowns, right? So that is step 2. So this is how, like I said, this is how you should be solving all the questions. So let's do knowns and unknowns for this. So I'm going to put a K for knowns, U for unknowns. So can somebody tell me the knowns for this question? So what lengths do we always know, or what angles do we always know? The input, I agree with you. So you would say theta 2. Sure. Is that R2, Jackson? Or is that just 2? Or everything about 2? R2 as well. I can agree with you there. And the reason why is because theta 2 is our input, so it is that right here. Theta 2 is our input, as well as R2 is some known length, right? We know that it is this long all the time. It does not change, therefore we can measure it and we know it, right? Let's try the next one. So Rosendo is about to get us something else. So what is another thing that we always know? I think there are 3 unknowns for this one. R3, Rosendo is correct. R3 is always known because it is essentially just on the edge of this circle. And it's all, no matter how this thing spins, R31 meets it right here. Because we drew it like that. We drew it to where it'll meet right here. And this is where, yeah. So R3, also known. Anything else? I'm running out of room. I didn't really think that one through, did I? Rosendo, give us another one. What's another one that is known? R1. I can agree with you there as well. Because R1 is just the length from this ground to this ground, and it is not changing. Bar some sort of hurricane or earthquake. It is not changing. So, we have R1 as well. Anything else that we know? There's one more. Theta 1, correct. So theta 1 is the angle of this vector. And since we put the coordinate system right on top of it, x follows that immediately or always. That means that theta 1 is always 0. So theta 1 is also known. Now let's try some unknowns. So the reason why I like doing the knowns first is because basically everything that's left over is sort of unknown. So it really makes a pretty, process of elimination, right? Something is either known or unknown. It's not really ever in between. So what is left then? What do we got left? And you can use So RC is correct. So RC is unknown. And the reason why it is unknown is because as this thing moves further or back, RC is going to get bigger. Because let's say it's at the end of it right here. Let's say that RC moves to here. Or that point, this revolute moves all the way to here inside the slider. RC has just gotten bigger by exactly this much, right? Plus D. So it's RC plus some distance, right? So therefore RC has just changed depending on how this thing moves. So RC is 1. I agree with you. Anything else? Junlin, don't answer. Anybody else here? Sean, Salem? Anybody want to get in on the action? Rashid? So there's not many variables left to choose from, right? Like we have theta 2, R2, R31, R1, and theta 1 as things that we know. So there's only like 2 more left that are, you know what I mean? There's only 2 left anyway. Theta 3, yes. So theta 3 is also unknown. And the reason is because theta 3 is essentially this right here, right? And so theta 3 is this line to here, and as this thing slides, right? Let's say it pulls back the way I wrote last time, and it hits the limiter here. This whole top part is going to move that way, therefore shallowing this angle to something like this. You know what I mean? So that angle has changed. So there's one more. One more. So we've taken care of 2. R3 and theta 3. R1 and theta 1. We've taken care of all that. So there's only one more vector left that we haven't talked to even about what the last one is. There's one more. So just the process of elimination. It has to be the last variable up there. Last man standing. Yes, it is theta C. So theta C. Theta C is the last one. And so basically how this one works is that, so once again, let's say we pull this all the way back to here. So theta C, well, let me draw that coordinate system. That'll probably make things easier to start out with. So theta C is essentially, let me try and draw. Let me get rid of some of this stuff so you can figure that out. So it is like this, right? And so theta C is, if you draw this coordinate system up here, which, like I said, I'm going to do it very poorly, so, you know, your results may vary. But essentially it looks something like this. Well, maybe, right? You guys can agree it looks something like that. It's basically, it's taking this line down here and moving it up. Now, obviously, mine's not going to be as great. You have to use a ruler to really be, you know, precise, but I don't have one. So this right here is basically our angle. And so you would take this. Oh no, that's theta 2, never mind. Not what I wanted. I'm talking about, let me see, so that right here. So that right there is theta C, right? So you can agree that theta C is right there. And so now what happens is that as this thing moves, so let's say this whole thing, let's say theta C, or let's say that this arm moves all the way this way, right? Or like somewhere way over here. If it moves all the way over here, that means that this part is now like, it looks something like this, right? Would you guys agree? It's now over here somewhere. And so the angle has changed in some way. And so I will actually, I know this one's going to be hard to see right now. It's kind of one of those ones that's hard to see, but I actually have this one on Autodesk, and I will pull it up just to make it, you know, a lot easier. But when it pulls up, oh, well, I was going to, where is it? Ah, here it is. Look at that. That was easy. So right here. So essentially, now obviously I didn't do a very good job making this, but essentially you can see that this angle is right here, right? So this right here, remember, is theta c, right? And as we draw this, bring this thing down, you would agree that during this time, the angle has changed a little bit, right? So now if we redraw it, this right here is where it's going, and that is sort of where we're at. You see the point? So the angle has changed, makes it a little easier to see, hopefully, doing that. Hopefully that helped. So it did change. And like I said, sometimes it really is helpful to do something like that, because it's hard to tell sometimes, because as you move it, it's hard to think about multiple things moving at the same time. And so, yeah, it always messes up, in my mind at least. So now it's time to see if we're right. So Yes, so right here, you can see, those are the unknowns right there. Theta 3.1, Theta 3, and R3.1, which are, remember, R3.1 and Theta 3.1 are RRC and Theta C, because that's how I did the numbering. But we are correct. So you guys are probably wondering, or maybe you're not, how many equations do we get out of this? Which come into the next part of this, which is the nope, not good enough. So the scalar equations, that is the third thing that we have to do. So we have completed steps 1, 2, and 3. The third one is the scalar equations. And the scalar equations, if you recall, are x and y, right? They're essentially the sine and cosine of all of these vectors put together. And so we will do that. I'm going to write them up here. So let's do 3. So this is 2. And the loop, I forgot to leave it up there, but I'll put it back. Well, somewhat. I need to pay someone to draw for me. I don't get paid that much though, so I can't do it. Alright, so here we go. So this is our loop again, R2, RC, R3, and R1. So the third part of this is to write your equations down, your vector loop, right? So for our vector loop, I'm going to write R2 plus RC plus R3 minus R1 equals 0, right? So that essentially is our vector loop, right? And now you guys might be wondering, why did I make the last one minus? So this is something that I've never gotten a good answer for, and I'm kind of ashamed to say that I really don't know how a lot of the times they select it. I have no idea. So like for example, in this question, it goes R2 plus R31 minus R3 plus R1. So the only one of them that is negative is R3. And I don't really know why. Maybe so, and I've asked multiple classes. I do not know why. So if you know, Jackson, please tell us, because I've never really been able to figure out why. It seems arbitrary to me. So is there a definite vector that needs to be negative? So what do you mean? Like, is there one that you have to put as negative, or else you won't get the question right? Could you have made R2 negative and R1 positive? Yeah, so you can flip around the signs, right? Because they did that example where they did flip around the signs and you still get the same answer. But I'm saying, like, I don't know how they choose R3 to be or negative. I've asked a whole class of 45 people to, like, do they have any thoughts? Or I've asked a TA that's taught it twice, and I've never gotten a straight answer. And I took the class and didn't get a really good answer. So I can't tell you why that one is negative in comparison to the other ones. But as I told you guys, that isn't really important, because if you wrote it like this, plus RC plus R3 plus R1 is equal to 0, and let's say R1 is negative, essentially you've wrote the same thing. Well, no, you can. You could have 3 of them added together. It's just that R1 could actually be negative, because remember, R1 is a variable, so it could be like, plus, and then it's actually just a negative number. You see the point? Is that so you can add negative numbers together and get 0. What I'm saying is this, like, you could have R2 as a vector, right? Plus RC as a vector, plus R3, but R3 could be a negative number, right? So you could end up you could get to 0 a different way. And you could write it, that's basically saying minus, you're right, if that's what you're going to type in. But the point is that I don't have a method of, like, getting this answer so that you guys can do it yourself. Like, you know what I mean? Like, if it was something like, if the vector is going up and to the left, make it negative. There is no rule that I know of that is getting these negative numbers. It seems arbitrary on all the questions. And so I'm not really concerned with that, like your signs in front of the vectors. No, it can be 0 because I've added a negative to it. So, like, let's put it this way. Like, you could do this with numbers as well. So, like, let's say we have 5 plus 3 plus negative 8. See what I mean? Like, you would get to 0 like that. But you're saying it's basically subtraction, because it's adding a negative. So it is subtraction. Yeah, so it is subtraction, but the thing is that because I don't have a method of getting you guys all the same answer, like, for example, I don't have a way, like, let's put it this way. If I told you guys this rule and said, if you go around this vector and it goes down and to the left, make it negative. If it goes up and to the right, make it positive, or whatever the ruling is. There is no method that I know of that does that correctly for all of them. And so I think that a lot of these were chosen arbitrarily. And I'm not going to punish you for you choosing arbitrarily. Like, for example, if somebody wanted to make R3 negative and the other one's positive, I can't tell them that they're wrong because I don't know how they got it, and that's the problem, you see. And if you, like I said, I've asked this to every class. I said, if you can figure out how they chose R3 as negative and why they have the other ones positive, then because let me tell you, yeah, no, you're just, so that's the problem is that I was this is something that I had whenever I was trying to teach the last time is that I couldn't give a straight answer because there was none that I knew of. I even asked my teaching assistant who had taught it twice or helped teach it twice, and I even asked him, I go, how do you know the vectors are supposed to be negative or they're supposed to be positive? And he goes, it's arbitrary. He even told me it's arbitrary. You can select either one of them. And I was like, okay, well, what if you make them all positive? And he goes, well, I guess you could do that. And I was like, okay, but anyway, whatever. So just real quick, guys, I'm not concerned with the signs really. I'm not really concerned, right? That's not something I'm like. I'm not. If you let's say if you put a plus here, and Jackson puts a minus there, I'm not gonna. You're not gonna get hammered for points like that. What I'm looking for is I'm looking for you guys to be able to do the process correctly, because there will come a part where you have to change the signs because you have to do derivatives, right? And sometimes, signs change. And so that's all I care about. Because let's put it this way, if there was a method that I knew of that got us these answers every time, and I'm going to research it, I'll try and find out again, then we could all do that, right? But until then, it doesn't really matter. Just as long as you stay consistent. Stay consistent. So like, for example, if you wrote this right here, and then on your next scalar equation, you wrote like R3 cosine theta 3 plus R1, even though it was a minus up here, then you're wrong, right? Because you flipped the sign for no reason. Just stay consistent. That is all I'm asking you. Does that make sense? Just don't change the signs for no reason. If there is a derivative that requires you to change the sign, then change the sign. But do not change it for, however you select the sign is up to you. But don't change the sign for no reason after you've selected it. There has to be some reason, some mathematical operation that got it to be a change. And like I said, if I find out how they selected this, I will let you know. But I've read this book during the part where they talk about that specifically, like how at the very first vector loops, and I could not figure out a way to do it. So, but like I said, I think it's arbitrary. I think you can select it however you want, and just put a minus sign on one of them, and you'll be fine. I know that sounds really dumb, but and it doesn't really make sense in my head either. But that's the way that we're going to do it right now. How about that? And if I can find out a foolproof method for everyone, I will find it. But I have yet to do that. Yet to find it, at least. So, real quick, I'm going to write out the equation. So the next step, like I said, is the scalar equations and the actual equation. So let's do R2 plus R3, 1. I'll just do what the book did, but once again, don't really know how they did it. Equals 0. And the scalar equations are the same thing, only with x's or cosines in here, right? So it is R2 cosine theta 2 plus R3, 1 cosine theta 3, 1 minus R3 cosine theta 3 minus R1 equals 0. And the reason why it's R1 is because R1's angle is 0 and cosine of 0 is 1. So R1 stays the same, right? Oh, yeah. So then let's do this. Now the next one is R2 sine theta 2 plus R3, 1. This is where it gets a little tedious. This was added, by the way. Sorry, I messed up. The book adds that one. And that last one goes to 0 because sine of 0 is 0. So this was the x equation, this is the y equation. So far, this is how you should solve the questions. You should go define the loop, so you make the loop, and you name the variables. You do the knowns and unknowns, which is here. You do k's and u's, which is theta 2, r2, r3, r1, and theta 1, and you find your unknowns. Then you write out your scalar equations, right? So now, real quick, this is where we've run into a bit of a snag. And you will find this in a lot of problems. How many equations do we have? And this one doesn't count, by the way, because essentially this is just a governing equation without like real directions to it. It's just the vector equation. So how many equations do we have? So this one, like I said, does not count. It's basically the same as this one, just broken up into components. We have 2, that is correct. We have this one and this one. How many unknowns do we have? We have 3. So that is a bit of a problem, wouldn't you say? We do not have enough equations to solve for our unknowns. But luckily, through the power of geometry and friendship, we will find there's one more equation that we can figure out, right? So this right here is, I think I brought this up last time about using geometry and using like angle changes and sharp corners to make equations to help solve. So if you look at our vector loop, right, which is right here, or look at their vector loop, that one's probably neater. If you look at their vector loop, whenever your first instinct when you have to find another equation is that you should look for sharp angle changes, like 90-degree angles or 180, like, a very like nice number. You should look for that and make sure it never changes, right? So if it's always 90 degrees, which this one is always 90 degrees as this thing turns, you should look for things like that. And the reason is because it's very easy to write an equation that gets you one angle related to another one by a sharp corner, right? So for example, if I wanted to relate the floor of my room's angle to my wall's angle, what would I write? I would write theta floor plus pi over 2 is equal to theta wall, right? Assuming my wall is, straight up and down and my floor is flat, right? I would say that basically 0 plus 90 gets you the next angle, right? 0 plus 90 gets you 90. And so you can do the same thing here. So you would say theta 3, 1, or theta c in our case. Theta c, which remember is this sort of angle. Let me try and get a better one for you. Something like that, right? And it is from here to here. Theta c, I think you would do minus pi over 2. Yeah, minus pi over 2 is equal to theta 3. Does everybody kind of see how that worked out? Because these two vectors, R31 and R3, share a common corner. And so essentially they have to equal each other with the corner's angle, right? So basically the addition of this angle or subtraction of this angle, which is this right here. So let's put it this way. It's going out on this angle. This angle is theta c. If you subtract off pi over 2, you get R31, right? Does everybody kind of see how that works? Hopefully. Anybody? Anybody out there? Is this thing on? Okay, did that make sense? Okay, it did make sense. Good. That's what I'm expecting. So that is our third angle. or our third equation right there. So let's put it this way. If you tried to solve this in an equation solver, it would come up with, it wouldn't know one of these, it wouldn't know one of the variables, right? When you did an equation, it wouldn't be able to solve for it. But if you add this equation in, what will happen is it will crunch them all together, and as the equation solver finds values for theta 3, it can then find values for theta c, because it is a relationship very easy. You add pi over 2 to theta 3 and you get theta c, right? So your equation solver would be able to do it based on that relationship. If you did not have that, it would not be able to do it, because it would have no way of relating theta 3 and theta c together. And so, right there, you get 3 equations, right? 3 unknowns. You can now solve for it. The whole thing is solvable. And this right here is something that you should look out for. Very, like, sharp corners most of the time means that you're going to have to add some sort of equation. Now, there are other ones that are more complicated. Like, for example, when, let me see if I could find one real quick. There is one down here at the bottom that I recall that is pretty confusing. Let me see. No, it's not on this one. It's on a different thing. But essentially that one, the one I'm talking about, essentially there's 2 vectors that are on top of each other. So like, for example, I'll write it out. I'm never gonna get that back, whatever. So 2 vectors that are on top of each other. So essentially you could write, let's say you have a link that is like this, right? And there's a pin in the middle, right? Some sort of pin joint. And so let's say that you have a vector that goes from here to here, right? From here to here. You don't know what that distance is, right? Because this pin can slide further or closer, right? You have no idea what that distance is. But there is a way for you to figure that out. And so you can relate the distance between here to here as a total length of this whole link, right? Because you guys would agree, if we know this whole length of this link, right? Because it's something we've created and manufactured, right? It's the same reason why we know R2's length, right? So we would know that. And then let's say there's another vector that, like, goes from, here all the way. So essentially you could create another equation that is like, let's say this is R1, right? And let's say the whole one on top of each other is like R2, right? Or not R2, but something else. Let's say that length is known. You could create another vector that essentially means that if you had these 2 added together, so let's say you had R1 plus another vector, which is like from here to the end, R1 plus R2 has to be equal to the total vector length, which is R3, right? And since we know the total vector length R3, that means once we figure out one of these, we can know the other one, right? Essentially, it's kind of like a very simple math problem that you guys have probably done 100 times, where if you know the total length, right, and you know one of the other lengths, the other one is known as well. And I wish I actually knew the question this is on. It'll make more sense if you actually saw what the question it's on. But let me see if I can find it. Nope, not that one. This one right here. So it's this question right here. This is the one I was talking about. So essentially, what ends up happening is that you have this vector here, and then you have another vector here. And so obviously, if you go R1 and R2, you would have to say R1 plus R2 has to be equal to the total length. And since R1 and R2 are unknown, right? Because essentially they are related, because obviously if this thing slides further this way, the other one gets bigger by that distance. They are related in that way. If you know the total length here, which we will know because it's something we created and manufactured, this could be like, let's say this is 20 feet. That means all the equation solver has to do is find one of these. And if it finds one of these, it finds the other one. You see what I'm saying? I hope that. So basically, I'm trying to give you other examples of things like when you're going to have to find additional equations, but it's hard to do. A lot of times you just kind of have to, you recognize that you're one equation short, and then you just have to go into your problem and try and find an area that you can relate to each other. And that's basically the best way I can help you, is that you just have to go and find like a sharp corner where they meet at 90 degrees, or where they share the same vector length or a total length, and you can relate them like that, distances versus angles. But yeah, that's basically it. That is all I can really help you with on how you just have to kind of recognize it. And now if we go down here, so they did it the opposite way. And by the way, this is okay too. So they did it the opposite way. They did theta 3 plus pi over 2 gets you theta 3 1. I did it the opposite. I subtracted it. But they're all perfectly fine. You could even write it like this, where they all equal 0. That is also fine too. And so then, this is the answer. So these are the things we just wrote up here, right? And theta 3, you have to make sure you write that equation. So this one was a fairly straightforward version of an extra equation problem. But remember, as you use more vector loops, you end up with more equations. So like for example, if I did another vector loop, you would have 2 more equations. So you'd have 4 total from 2 vector loops. But if you have to use 2 vector loops, generally it means that there's a lot more variables. So you might have to do multiple of these. Like there might be 2 sharp corner equations, or there might be something else, like a rolling contact equation or something. So there's plenty of things to get to when it comes to that. All right. So next time, so Friday, we are going to touch on probably rolling contact. Yeah, we're going to have to do rolling contact. So rolling contact, and then at the end of the class, once I go over all the rolling contact equations, which I don't think they don't do much in this. Well, yeah, they're right here. So once I touch on all the rolling contact parts, then we will look at a more in-depth example, which is this right here. So this is the more in-depth example. And so this one right here, spoiler alert, requires 2 vector loops. You could probably do it in 1, but it would be really painful. So there's no reason to do that to yourself. Just use 2. So this right here is what we will be doing. So if you have this in your head, start thinking about ways that you could create the vector loop. I'm going to take attendance right now. I forgot to, so if you want to stick around for that, you are more than welcome. If you're not, that's cool too. Whatever, I just couldn't find it. Give me 1 second. All right. Da, 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 da.